So, we continue our live stream for the AnyLogic conference. Welcome to those of you just joining us. I'm pleased to introduce Dr. Jeff Martin, from GHD, who will talk on green hydrogen supply chains. Take it away.
Thanks, Gavin. Yeah, I'll say a little bit about myself. So I'm the simulation lead at GHD Advisory, based in Australia. By background, I'm a mathematician, so I guess I'll talk about topics like engineering and economics, but I'm not an expert on any of these. So I guess that if that affects the questions that you're going to ask. But I am an experienced AnyLogic user. I've used it to simulate lots of different industries, and one of the most recent ones being green hydrogen supply chains, which are very popular at the moment. So I'll start by explaining a little bit about what makes a green hydrogen supply chain. So there are many different colors of hydrogen. So green hydrogen is where you generate hydrogen without emission of greenhouse gases. So essential ingredients are water. So you're going to take water and split it using a lot of electricity into oxygen and hydrogen. That's essentially it, using electrolysis. And what makes it green is that the electricity you use has to be from clean energy sources. So you're talking solar and wind generally, or anything renewable. Then, in terms of what you do with the hydrogen, you can sell that directly as liquid or gaseous, or you can synthesize that. One popular thing to do for transportation is to synthesize the hydrogen with nitrogen and create ammonia, and then that makes it easier to transport over long distances by ship. So I guess one of the key things when evaluating the feasibility of hydrogen supply chains is being able to compare different across different projects, different sizes, different lifetimes, and capacities. And the one way we do that is using levelized costs. So we measure the costs over the entire lifetime of the project and divide by the amount of hydrogen we produced, and that gives you a cost per kilo. So we call that levelized cost of hydrogen, LCOH. And right now, the government in Australia has a goal to produce hydrogen under $2. So H2 under 2 is the kind of catchphrase. I guess I don't know exactly where the 2 comes from. It's kind of a catchy way to put it. I think the reasoning is essentially that if we can produce clean hydrogen for under $2 a kilo, it'll be competitive with today's fossil fuel derived energy sources, and then you'd be mad not to use green hydrogen. So what I've been doing a lot of is assessing feasibility for different hydrogen projects. So a lot of people want to get into producing green hydrogen, and so you really have to evaluate the feasibility both from the engineering side, actually designing the plant and the supply chain, and evaluating all the risks and working out what the markets are, and then you've got your financial. So the business analysts need to know about the financial side as well. And typically those were done by different consultants. You'll have an Excel model for your financial model. Then the engineers will create a report and some design diagrams, and they'll be generally pretty disjointed. So our approach on this was to combine the financials and the engineering into one model, and so we can really link the engineering design scenarios directly to the business value. And so one way we do that is using AnyLogic. We use dynamic simulation, so we can actually capture the complexity and risk. So it's not just a static Excel model. And we add a financial layer on top. And so that really allows it to reach the executive decision makers. So because no executive has ever looked at a engineering design design sheet. So we can have interactive deliverables and animation, which really makes it a lot more tangible, and you can produce nice interactive charts and things. So what exactly were the scope of the modeling? I guess you've got your key decision variables on the left. What are the products we're making? What are the markets we're selling to? What locations are we based in? That'll change all your input costs. What are the processes we use? So that's where you really need the engineers. What technology are we using? So, sort of, if you go from left to right, from the inputs through to the outputs, I guess the first stage is working with the engineers to really design the plant and the supply chain, getting all the specifications for all the assets. What is the um, design capacity? What's the availability of the assets? How will they all fit together? What capacity should we use? Um, how are we going to transport it to the client? Then you capture all the costs. So you've got this cost layer where you capture capex, you capture opex um, over the entire lifetime of the project. Then you've got the financial layer on top of that. So you've got all the costs coming out of the model, and then you need to basically, you can get a balance sheet of over the entire lifetime of the project. And so that's where all the business elements come in. So you've got your weighted average cost of capital. So you can actually take into account the time cost of money, and all the other things like what are the tax considerations, what's the value of the assets at the end of the project, and so on. Are there any grants and offsets you can take advantage of? And then at the end, you've got basically the economic evaluation of the whole project. You can capture the risk, um, and you've got the design that you're going to take forward to the next phase of the project, or it could get canned at that point. So I guess the question is, why use AnyLogic? So typically this is all just done on static reports and then a Excel financial model. So why bother with AnyLogic? Um, I guess the first one is that it's dynamic. So one of the interesting parts about green hydrogen in particular is that we have renewable energy, and most of the cheap sources of renewable energy are variable. So they vary by time of day and by weather. So being able to capture all of that variability is really important to accurately assess um, the feasibility of the project. And we can also capture the asset availability as well. So being able to um, capture planned maintenance and unplanned maintenance in the model to actually get dynamic asset availability, because when you stitch all the parts of a supply chain together, you don't have availability all the time. So you're going to have losses, and to accurately capture that, you need a dynamic model. So, I mean, typically in the past, engineers would just be like, I reckon about it'll be available about 8,000 hours a year, and that's the extent of the consideration of variability. Um, we use the fluid library, so it's really easy to capture. So any system with product flow, obviously hydrogen being one of them. You've got a lot of gases, liquids. We just use the flow library to model all of that. It's really easy to bolt together components, and it'll automatically work out the flow through the system. Um, it's modular, so we can break the supply chain down into components and switch things on and off depending on what scenario we want to evaluate. So, different capacities we might need. If beyond a certain point we need more water, we need to turn on a water desalination plant, because then we exhaust our water supply. So you can switch that on according to certain triggers. We can turn on, do we want to synthesize ammonia and sell that in this supply chain, or do we want to liquefy the hydrogen and sell it that way? So it's really easy to stitch. Once you've got all these components, it's really easy to stitch them together in a way that's going to be a nightmare in a spreadsheet model. It's quite visual, so it's interactive. It's a lot more engaging for clients. It's something that an executive could actually look at. And I guess the sort of the nerdy part of this, from an experimentation point of view, it's a lot more traceable. So we can use version control on the models in a way that's a lot easier than a spreadsheet is. And you can separate the inputs from the logic, so it's all very traceable. So there's no sort of magic numbers that sit inside there that you can't actually change. Everything is really transparent. All right, so I'll show you a quick run through of the model and explain sort of how it works. So I guess this is sort of the production layer. And on the left, you've got your key inputs. So you've got water, you've got air, and electricity. And then we sort of, each part of the supply chain that's turned on is sort of highlighted, and the grayed out bits are turned off in this scenario. And you can see we've able to capture buffers. So you've got storage capacity, and you can see that dynamically go up and down if I play this through here. So the buffers go up and down, so you can actually assess, how much storage do I actually need, rather than just sort of rules of thumb. We can, for the electrolysis, which is one of the biggest costs involved in the supply chain, we can actually easily scale those up and down in terms of capacity. We can consider different technologies. So there's roughly 3 different types of electrolysis technology. The main one being alkaline, but there's also PEM electrolyzers, and there's sort of other technologies as well that are being developed. Solid oxide. So we can consider all those 3 different technologies and put their specifications in the model, to the point where we can capture, the efficiency of the electrolyzers, which change dynamically. So as the power goes up and down, as the load goes up and down, the efficiency changes. It also degrades over time until you get to a point where you refurbish the electrolyzer, and then the efficiency will improve. So we can go to a high level of detail if required, depending on the stage of the project. We can also even put in different vendor data here, so we can get details from particular vendors, and set up the model to run with those specific inputs provided by the vendors. So you can really make it quite accurate. Then this particular option has nitrogen as well, not ammonia synthesis, which takes this nitrogen from the air separation unit. And if I just play this again, we can see that we're capturing the dynamic availability as well. So this has gone into maintenance, and you can see that our buffers start to fill up because we've lost downstream capacity. If our buffer filled up, we'd actually have to shut down our units upstream. So it's capturing that dynamics of the system that most models aren't able to capture. All right. And one of the other key inputs, so the biggest OPEX cost to generating green hydrogen is power. It requires a gigantic amount of power. And if you want to make it green, it's got to be from renewable sources. So basically, they're variable. So we have to actually, most production plants will run at 100% utilization, because you paid for expensive kit. You're going to try and run it as much as you possibly can. So you want to keep it running as much as possible. The problem with green hydrogen is that the power supply is variable. So if you're looking at large scales, I mean, small scales, you can potentially connect to the grid to get a firmed contract for your power and run it at pretty much 100%, depending on the availability of the assets. For large scales, there's no hope. You really are forced to sort of respond up and down based on the provided energy from your renewables. And as you can see from this, that we're sort of maxed out at load at this point, but the actual supplied energy is way more than that. So you've got a lot of surplus energy, and so it's a trade-off between what's the utilization of your actual assets compared with how much over generation do you want to produce, because obviously this is you'll have to find another way to get rid of this excess energy. So that's one of the key considerations, and currently, by far the biggest cost, particularly at large scales, is the power cost, which is making it sort of not very feasible at the moment. Okay. And I guess on the other end, so I talked a bit about the engineering side of the model, but uh, we we basically connect up the outputs. We can run using the Python library. I don't know if any of you saw the talk earlier today on the Python library that can connect up to AnyLogic. We use that to post process the outputs. To basically run all the cost values into our financial model, and we can get cash flows, um, levelized costs, MPV, ROI, those sort of financial metrics. And we can put it in a dashboard so you can sort of look at different scenarios, you can compare scenarios and look at the values over time. All right, so I guess a couple of these I've already mentioned, but sort of a summary of the key model uses. I guess sorry that I can't share like actual results because that's all confidential, but I can talk about the kind of things we tested with the model. And one of those is the trade-off between generation cost and plant utilization. So I guess I put in this chart to sort of demonstrate how that how the utilization changes for different renewable profiles. So this red line here is 30% utilization. So that's just where we've got solar generating our energy. And so you can see that sort of this is I've averaged over all the days. So you can see the average profile. Obviously, you're only going to get solar energy during the day. So most of the time, the electrolyzers are going to sit idle. So we're only getting 30% utilization. And then if you turn on some wind, so wind, particularly in this location, is complementary. It's particularly generates energy at night. So it's a good complement for solar energy, which obviously only produces during the day. So as we turn on more wind, so that we get 40% utilization, and we can actually run the plant at night as well. And you can sort of see how that increases as we increase the utilization. We turn on more and more wind, increase the solar as well. And then to get up to sort of 80, 90% utilization, you need batteries because there's going to be periods at night where there's no wind and obviously no solar, so you have no energy. So the only way to get up near 80, 90% utilization is to use a battery in those circumstances. And then you're starting to get, you can see the peak here is way above what we actually need. So it starts to get cost prohibitive to reach those high utilizations. So generally about 70% utilization is the sweet spot. We can compare different market pathways. So obviously it depends on who is buying the hydrogen and how they want it, but the hydrogen market in most cases is still developing and technologies to use it. But depending on the different pathways, liquid hydrogen, sell it as ammonia, gaseous truck refueling, all those sort of things you can consider. We can compare vendor technology, which I've mentioned, and we can understand the key drivers. So, CapEx is a big one. So electrolyzers are very expensive, but they're coming down in costs as sort of the global production capacity goes up. It's expected to cut the cost, like in the same way that solar has come down a lot in cost. It's expected that electrolysis will as well. So we can understand the key drivers and try to chart a pathway to under $2 per kilo for the levelized cost. I guess the other problem with this number is like, what does the $2 refer to? So you can, depending on where the boundaries of your costs are. So I assume $2 is probably just the cost to produce the hydrogen. You've also got, of course, the cost to get the hydrogen to the customer, which can be significant. So a lot of numbers bandied about, but they're not much information about what they actually mean. All right, so I guess I'll say a little bit more generality about the sort of approach. So for this project, it's sort of pre-feasibility, so it's sort of sitting in here in terms of the life cycle. But this sort of approach can work across the entire life cycle of the project. Obviously, you'll get more accuracy as you sort of rule out different options and you get more detail. And once you reach actual operation, then you've got a lot of data and you can use the model you can refine the model further to actually optimize the processes and debottleneck everything. So you can apply this at different stages and flexibly update as you go along. But obviously your ability to influence changes is the highest at the start. You can knock out infeasible options really easily, and it's quite cheap. You've got less opportunity once everything is already in place. Seem to be going pretty well with time, and this is my last slide. So I guess just at a high level summary for the approach, because I think that the traditional approach leaves a lot of value on the table. So it's often quite disjointed, different people, different work streams, different people building different models, and the assumptions are never aligned. So one of the key values of the way we've modeled this is that the model provides a single source of truth. So it combines the assumptions from all the different work streams and gives you the business outcome. So there's no debate about what did we assume for all of the different parts of the supply chain, because the assumptions are transparent. And we can link the engineering scenarios directly to business outcomes. So typically engineers are good at considering the technical feasibility, but they won't consider the business outcomes. So then, they'll just design it and they won't, um, they're not really considering the overall cost of the project in terms of how they're designing the plant. They'll design it so it works, but not necessarily optimizing those sort of business decisions. And using AnyLogic, we can capture uncertainty and variability. So it's not just static values. Typically, a lot of business cases will be like, oh yeah, we'll consider a range. We'll have a low, medium, high, and then everything for the low side, everything will be low, and for the high side, everything will be high. It's not very sophisticated, so we can actually have a distribution on different inputs. And then a distribution on outputs. As I mentioned earlier, dynamic asset availability. So you can really see as you combine different parts of the supply chain, how do they perform and capture the dynamic losses. Fast iteration of scenarios. So already, just being able to switch things on and off and being able to change capacity up and down, because we have business rules embedded in the model to say, how does the cost scale as we move up and down capacity. So we can do that really quickly. We've got the financial layer in as well, so we can capture the time value of money, discount rates, inflation, all of those things, technology learning rates. So potentially, as we scale up, capacity should come down in cost. And we can understand storage capacity as well. All right, so that's pretty much it, and that's pretty much time.
Thank you, Jeff. That was very informative. It's great to see that these renewable energies are matching the intense energy demand of producing hydrogen. There's a couple of questions that are coming from the audience. There's, if we can have a quick look at those, I think we've got time. They should have come up for you. Have you got them there?
Yep. All right, so I'll read them out. So,
Okay.
are the technologies selected, or do they run independently of each other? So, I'm not quite sure what you mean by run independently. So we can mix and match. So, but basically that's a model input. So we can set up the model to run with any different technology selections and compare them. We can run them alone, or we can run it as a mix. If you want to test out both PEM and alkaline electrolyzers, for example. I hope that answered your question. Was there any need to calculate the energy in versus energy out efficiency? So yeah, it's not very efficient. So I guess there's products out there to kind of like use energy as a short-term hydrogen storage solution like a battery as well. That those solutions exist, but there's a huge loss of energy going in and then coming out again. So and it's slow to charge and discharge. So there are technological issues there with those sort of solutions. I guess in terms of comparing it to other energy sources, it's really so I mentioned levelized cost, but yes, you can also compare it to the levelized cost per gigajoule of energy. So that makes it easier to then compare across different energy sources. So you can easily go from your cost per kilogram of hydrogen to cost per gigajoule of energy. So that's something that's also important.
I have one more here. It's what criteria we use to determine the optimum energy mix of the solar, wind, and so on, and how is that optimized?
Yep. So that is based on cost and I guess the sort of utilizations you can get out of it. So we used historical data and then estimated costs per kilowatt of energy for each of the wind and solar. And you can, based on the particular region, you can get the capacity factor, so you know roughly how much it's going to generate. We used like 5 years of historical data, and that sort of tells you what sort of energy profile you're going to get. Now, obviously, when it's more than your maximum load, that's inefficient because you can only use up to your maximum load. So it's really, we evaluate it based on the cost to produce the energy and then what utilization you would get on your electrolyzers.
Great. One question I had was you mentioned that the model brings together the engineering and kind of the financial or economic side of this. Who might expect to directly interact with the model? Who would be sort of taking information from it and informing their work with it? Would it just be the engineers, or would you who might typically interact with it?
So I guess it's everyone really. So we work with the engineers to come up with the inputs to the model, and so that's important. So I'm not taking away any engineer's job by building a model of engineering. Basically, all the assumptions come from the engineers, and then on the other end, because the model's spitting out financial outcomes, I work with the client business analyst. They would be looking through the actual outputs to the model.
Great. Well, thank you very much, Jeff. I believe that's all the questions we've got. Oh no, we've just got one last one. I think we've got time for one last one. Have you had any runtime issues with the fluid library?
It really depends. So I guess it's dynamically updates, right, to every little change. So how slow or fast it is really depends on how often you need to resolve. So I guess old school simulators used to use teaspoons, which was slow, but I guess it never blew out because it was always consistently slow. So it really depends. Actually, yeah, it can be slow when you turn on lots of different pathways, and then particularly if you connect it up to like small little batches. So if you have little trucks that can interface into continuous flow, if you've got little trucks, that's obviously going to be really slow because you're batch filling them. Whereas if you've got like a pipeline and it's just consistently flowing, nothing really updates very often, it's really, really fast.
Great. That's all we've got time for. Thank you, Jeff. If people have still got more questions to come through, then please find Jeff on the platform, and I hope we'll stick around for the discussion there on the SpotMe platform. Thank you very much.
Excellent. Thanks.